So we now have some of the basic equations for phasor description of voltages and currents. They're rather complicated. I don't want to use the word complex because it's not meant to be a pun. But in this case, what we're going to do is we're going to look at when R and G, R is a series resistance in the line, G is shunt conductance, when those are small compared to omega L and omega C. Recall that L and C really control the wave traveling down the line. So let's look at the math a little more in the next slide, remembering that gamma is equal to alpha plus J beta. All right, let me step out away here. You don't have to see my beautiful face for the moment. Substituting gamma equals alpha plus J beta in our solution, which you see in the first line, gives me the second line, which is HB8, Hayton-Buck, at 8th edition, number 48. And you can see right away here that you've got alpha Z. So there's the alpha, that's decay, that's our usual J beta Z. And here is the same going the other direction. Now, if we multiply the phasor solution in 48 by e to the j omega t, take the real part, we get the instantaneous real voltage, and we assume that the amplitudes, B naught plus and minus, are real, we get the result 49. And the interpretation is shown on the next slide of 49. Let's look at the interpretation of that last equation. The first term is term 1, V0 plus. Amplitude of the forward traveling wave, e to the minus alpha z. Attenuation as a function of z. And then cosine omega t minus beta z. So that's for the forward traveling wave. It's a sine wave. It has our classic form of f of t minus z over v, as we know, and it is decayed as a function of z, not as a function of time. Damping, traveling. It's a fairly complete description of the wave. What about the wave coming back, the reflected wave? Well, E0 minus e to the, now it's plus, cosine omega t, let's go over here, minus beta z, with a plus, not minus. Okay, so what do we know about this term? That's our wave traveling backwards, plus sign. It's f of x plus vt, or z plus vt, or t plus z over v. Remember from our exercises in class that it doesn't matter if the form is written like this because a scale factor comes out. This is a wave traveling backwards. What about this? Why is there no minus sign there? There's no minus sign there because we're going in the direction of decreasing z. Z is decreasing, so there's an implicit negative sign here. And when z is less than 0, away it goes, decays away. So z is decreasing. That means wherever we are, this is going to be decreasing away, going in the negative z direction. Now, let's look further then at what we're going to do with this. Alpha and beta, big mess because they're related to gamma. If you remember, gamma is equal to square root of r plus j omega L multiplied by g plus j omega c. So it's multiplied. So this term times that term square rooted. And now we have to take the real and imaginary parts of this. In general, that's a mess. So we're going to look at the main idea here because we're low loss. And in the low loss case, R is much less than omega L. G is much, much less than omega C, so we take things apart piece by piece. And first of all, for alpha and beta, we use a binomial expansion on that and expand it out, keeping the first couple of terms. And for Z, which has the ratio of those square rooted, similar idea, but we're going to also have to use the expansion of 1 over 1 plus x. And that gives us the equations listed. So now, what have we got? We've got our first transmission line model. It's got propagation. It's got complex numbers. We know how to go instantaneous. We know the phasor. We know the complete complex solution. We even included damping. And we also have simplified, as we'll see in an exercise, the values of alpha and beta for low loss lines. And now we can then focus on the interpretation of the dynamics of the line, starting with the most important one, power. No power, no nothing. So let's look at power next.